I asked to get this domain, or which is equivalent to find the asymptote. So we are going to take a look at problem number 14. And since it has denominator 3 plus x, then I need to make sure that this is not 0. So x is not equal to number -3. And that's what we say domain of the function is. So whatever is in denominator cannot be equal to 0. Well, why don't I graph this function? We also last time saw how you could graph functions using a calculator. So today I'd like to show you how to graph them without a calculator. So how to find the asymptote for this function, which is x is equal to -3 by just looking at the given particular little equation with denominator, and right away you get that asymptote. Now, when you're graphing this function y, which is equal to 5x to the second power divided by, I'll write it as x minus 3. I will write it. Good morning. It's good to see you all here. So I'm glad that you remembered about this nice Saturday class. I hope you are enjoying it. So anyways, let me graph this function. Good morning. So we're going to produce another asymptote. Good morning. So we're gonna divide our numerator by our denominator. It turns out that this be the way to find another asymptote, to actually get a how can you fix your audio? Just make it louder, right? Unmute yourself. Oops, I think I wrote it to somebody else by accident. So anyways, you divide in x into 5x squared. So you go 5x times. So this is going to be a product of 5x and x, and which is exactly 5x squared on the first place. So I put it here underneath, but then we're going to get a -3 times 5 is 15 multiplied by x. And then I'm gonna subtract, so that first terms are going to cancel, and the sign down below is going to change because we're subtracting the negative. So we get a 15x here that is left over, and all you have to do is multiply a letter x by number 15. So we're going to go positive 15 times, right? So this way I get the new number. So I'm gonna multiply this back, and we'll finish up with this division process, because now I get exactly 15x under the 15x, and then minus 3 times 15 is 45. So when I subtract, then this 15x will cancel, this sign with -45 changes to positive. So I end up with a remainder of 45. So here's our new expression for this function. It's 5x and plus 15. And there is also number 45 that I'm still to divide by x minus 3. So once you have this result, and this is going to be y, and this is going to be 5x plus 15. So this is all we need for this division. So looks like now I can see what we have the for the asymptote. So it looks like what we're going to do is get the y, which is equal to 5x plus 15, which is going to be called as a slant asymptote. So the line that somehow passes through point 15 on the y-axis. So looks like we've got the result, and that's really going to help us a lot to produce a graph. And usually to produce graph, we need a couple of points. And turns out that for this particular case, just 1 point should be enough. And this be the point of intersection with x-axis, x-axis intercept. So when you have the just a second. So anyways, looks like we need to recall definition of the asymptote or intersection with x-axis, x-axis intercept. It's happening when y is equal to 0. So in other words, when I set my numerator 5x squared equal to 0. So anyway, somebody is so anyways, looks like we are going to have 1 point of intersection with the axis, with our x-axis, and the graph then is probably somehow going to go in such a way that we have one branch of it passes through the point 0. So anyways, so if somebody's computer is not working, I guess you probably should get a device, and somebody keeps telling me that she cannot hear anything, so she just needs to increase the volume. The best I can say, just get if your device is not working properly, well, you should get a free computer in the library, because I mean, they have plenty of free devices. I know it is kind of annoying to drive to the college, but the library is open and you can just go there. But anyway, so let us continue with this and see what else is supposed to be done here for the graphing of this little function. I think that my graph is a little bit deceiving. I think I need to, I guess, I'm sorry, I got involved too much with this chatting and I wasn't paying attention to the exercise. I need to redo this a little bit more carefully. The line is here a little bit lower, like that. So I think not even like that. It's see, it is important to actually put the correct location for the asymptote. I believe it goes somehow. Let me double check what I did. 3x and then 15 and then yeah, I think I did it. Looks like schematically correctly. So I put those asymptotes and then I need to see the points of intersection of my function with the axis, and looks like the one point of intersection with the axis should be 0, right? And that, I think I still have to be careful with this line. It will be somewhere here. Okay, I'm glad she will go to the library and get that laptop, because sometimes, yeah, sometimes those computers, they break, and I experience this all the time with my computer. So it's disappointing. I just went to the repair shop and had to redo the whole system. And I'm glad that this knowledgeable gentleman was able to help me very well with that. But yes, things happen and you never know, because looks like these computers are not of very good quality. You probably noticed that. Need to replace them every once in a while. So anyways, what I'm trying to do is make a little bit better picture. Same thing, but in a little bit better format. So now I'd be able to finally get a graph. So we have intersection with the axis, which is here, point 0. So I need to approach to my asymptote upwards to the right and upwards along this vertical asymptote. And since there is only one point of intersection, the other piece of the graph must be somewhere in this region, because it cannot be here, because if it is there, then it'll hit my intersection with x-axis once again, but it can't be done because of the issue with the only one solution, because we have a x equal to 0, the only intersection with our x-axis. So if you have only one intersection, then you don't have any more. So the other branch is down below, because it cannot cross your axis again. So that's what one needs to watch out for. And also, there is one more interesting observation. Notice that here we have x squared, which is equal to 0. X squared is equal to 0 means that we actually have so-called order 2 solution. It's just like when you were working with the parabola, when we graphed that nice U-shaped curve, like y is equal to x squared. And if I decided to try to find the intersection of it with my x-axis, so I set y equals to 0, I will get identical case of x equal to 0, but since it's also raised to the power of 2, then we're going to have so-called touching the x-axis intercept. So it's touching it. The function goes towards the x-axis and then bounces back. It doesn't really intersect it, but it just touches it. And that's exactly what happened here at the point 0, because of order of that solution was 2. This is something that we need to, well, I guess just every once in a while pay attention to. So let me try another graphing exercise, because today I'm going to be doing lots of graphing. In fact, this entire chapter is all about the graphing process. So I'm going to take a look at exercise number 23. And this exercise will have another function with denominator to consider. It's a function y, which looks like 3/4, and we have x squared minus x minus 6, so I can write it as x minus 3 multiplied by x plus 2. So what I'm doing is I'm factoring my numerator, and I also factor my denominator. And notice that denominator nicely factors with x minus 3 and x plus 3, because we have so-called difference of two squares, like x squared minus 3 squared. And we always factor it with a difference multiplied by the sum of these values. Or it could be the sum times the difference, doesn't really matter. So, of course, I'm going to start out with domain, because I need to watch out for my zeros. And looks like there are two numbers that I need to make sure are not used in the domain, such as a number 3, because it makes x equal to 0, and also number minus 3, right? Just like we had on the quiz last week. So we watch out for zeros of denominator. Besides that, I can actually cancel x minus 3 with x minus 3, right? So that's very interesting. We're actually going to graph not that big looking function, but just 3 times x plus 2 divided by 3 times x plus 3. So when I simplify this little function, it's actually not 3, but 4. Should be careful. I need to wake up. 4. So it's 4 times x plus 3. So then I'm going to have the only one vertical asymptote at x equals to negative 3. And that's our start for all of these problems. You want to get yourself vertical asymptote. Please notice that it's only one, because the other possibility canceled, which made life easier, and this is great. So now I need to also look at the horizontal asymptote, and horizontal asymptote, remember, will be a quotient of my numerator by denominator, just like we did in the previous example where I had to divide all that to produce the equation of the asymptote. So whatever the quotient is. So notice that when I divide, then since my powers are the same, then all I have to do is put 3/4 as my horizontal asymptote. So 3/4 will be here. And that's interesting to realize that if you have same powers of x, you don't really need to divide, but take whatever is multiplied by those powers of x and declare it as a horizontal asymptote. And then the last step I need is to see the intersection with x-axis, or so-called x-axis intercept. Notice I follow the same footprints as I did in the previous exercise. After I found those asymptotes, the next thing to do was to get this intersection with x-axis, right? So I set y equal to 0. And that means that I just need to worry about my numerator only equal to 0, which is going to be x plus 2, because denominator is never 0. We just said it's not equal to 0 in our domain. So we just make sure that x plus 2 can be 0, or x is equal to negative number 2. And this is someplace here. And that's my only point of intersection with x-axis. So that's why I have to go along my asymptote somehow like that. So that we go down to -3 and to the right to that red asymptote. And analogously on the other side, we have two branches that look like that. So keep on graphing, and one may say, so what? What can we do with these graphs? Well, it turns out the next section shows you that these graphs are very useful in solving inequalities. So if you consider the inequality, which is your function r of x. So let me give you an idea of the next section that I want to look at right now. So if this is my function r of x, which is 3 times x squared minus x and minus 6 divided by 4 multiplied by x squared and minus 9. And now if I graph the function again carefully with the asymptotes, so here's 1. So I'm just copying the same graph, but I want to notice one more very important detail. I just didn't want to fit it there, so let me get a bigger picture. So if you think that this is a graph of original function r of x, the answer is not really, because what I just graph is this little one, right? And what that little simplified equation misses is the fact that x is not equal to 3. So actually, at a point 3, I must have a hole on my graph. The reason is that, remember, 3 is out of the domain. At the picture that I have on the right, we had only -3 as a problem point because of asymptote. But +3 is also an issue. So that's the place to watch out when you cancel something out, because when you cancel, there will be no vertical asymptote. So anyways, I want to continue with this, as I said, in solving inequalities in the section after the next one. So once again, since this class is only 3 units and a textbook is produced for actually 5-unit class. Remember, the name of this textbook is pre-calculus. And the pre-calculus is actually the next class after this one. Pre-calculus is called Mac 1140. In fact, Mac 1140, the next class after college algebra, is what I'm going to teach over the summer semester. And I would highly recommend you to sign up for that class, because I'm going to use exactly the same book. And those sections that I'm skipping, like right now I moved to 4.4, and what we did was section 4.2. So what I did, I skipped section 4.3. So all of these missing sections will actually be covered in Mac 1140, because our college decided to pull some stuff from pre-calculus book and call it as a college algebra. And then the missing sections, along with sections that we already covered, will be placed in the next class, which is Mac 1140. So I would recommend you to sign up for that class as soon as you can, because you will easily pass it, since we're gonna go over exactly the same material with exactly the same book, maybe with a little extra, but I don't think it'd be an issue to actually quickly learn, because you will be fresh on college algebra. And so far, I think everyone in class is doing well, so you're passing it and actually getting a good grade on it. So I think that you're ready to move on and sign up for next class. So think about it. And I think that'd be very useful to have extra math class on your transcript, right? It's always going to look impressive for transfer if you want to transfer to some 4-year school. And anyways, think about it, and I will look at what's in the next section, 4.4, that just continues with more graphing. And in addition to graphing, it shows solutions for so-called inequalities. So it works with the various graphs. Let me utilize example 1 here. They already have a nice picture in it. And in that example 1, they produce a graph of cubic parabola. You probably recognize that cubic parabola because the degree here will be 1 and 2. So it's analog to y to the power of y is equal to x to the power of 3. So the cubic parabola that has one end of it pointing up and the other pointing down. Remember, that's what we had in the midterm, right? So here's the same thing. One end goes up and the other goes down. So what they actually did is they found intersections with x-axis. How they found them? Well, the usual way, they set this equal to 0. When they set the equation equal to 0, then you can see that -3, the first one, is here, point of intersection with my x-axis. And from the second parentheses, we have number 1, right? So that's our cubic parabola with one end that goes up and the other down. When they graphed it, they made sure that at point 1, the function touches the axis, because when you have x minus 1 squared, it means that your solution, when you set it equal to 0, is 1, but because power is 2 that it comes with, then this graph will be just touching, not intersecting the axis. And for the first factor, which is x plus 3, when you set it equal to 0, you do get -3, but since it's raised to the power of 1, or actually no power, so say first power, then the graph is just going to cross through that point, not like go down and then bounce back up. So that's an interesting little fact about graphing that helps us out. But the key part of this solution is that we are trying to solve inequality. We're having this product greater than 0. In other words, my function y is greater than 0, and turns out it is greater than 0 everywhere above x-axis, except for this point and except for that point, because that's where it is equal to 0. Everywhere else, and they say from -3 to +1, so in between of these 2 points, and then from 1 and up, from 1 all the way to the right, it's greater than 0. And you can see on the picture, the graph, the part of graph, which is greater than 0. What does greater than 0 means? Well, all the points on the highlighted piece of graph have their y coordinates that are greater than 0. And that's exactly what we mean saying y is greater than 0. That's why we call this whole left side as a y, or function f of x. So that's what they're explaining here in this little example. And that'd be our goal for this section. Graph, and then do one more step. See when it is greater than 0 or smaller than 0. Like if I go to the end of this section and try to do some exercises. So let me do problem number 19. I want to get some room for it. Let me share a board with you because I don't want to fit it in that little margin. Let me get some room and try to do number 19 exercise here, which is dealing with a x minus 5 in the parentheses squared, which is multiplied by x plus 2, and this is smaller than 0. So I got this product of 2 factors, and looks like this is going to be another cubic parabola with one end going up and the other going down, because again we have 3 parentheses here multiplied. Let's say, Alex, I see only 2. Well, but first one is squared, right? So we got a squared, and then the other has x, so it'll be x to the 3rd analog. So when I look at values, when my function y is actually equal to 0, so if I say it's y is equal to 0, because I need to get its intersections with x-axis. Remember, x-intercepts we defined as y equal to 0. So we get a pair of points that should be placed on my x-axis, such as 0.5 and the other point -2. So one end of this graph needs to go up and the other goes down. So it looks like at 0.5 I have the graph that points up, and at 0.2 I have the graph that points down. and then I need to carefully connect them in such a way that the function touches x-axis, because again, you see the power of 2 of my parentheses, right? Since power is 2, then we touch at that number 5. So the equation is, when is it less than 0? And the answer is y coordinates of these points less than 0, without including that end. Again, whenever it's less than 0, we have to consider the part of graph below the x-axis. And then I can describe this as an interval from minus infinity all the way to -2 without including, because I have to always pay attention to only x coordinates, because my original inequality had only x's. So for the part of x-axis with coordinates to the left from -2, I have the points on this highlighted portion of my parabola. So we don't do anything new. We just keep on graphing with one little extra step. We check when we're below or when we're above the x-axis. Notice if it's less than we're below, if it's greater than we're above. So let me do another exercise. Let me go back to the textbook and try to graph one with denominator. How about exercise number 34? So I have to, again, take a function and graph it. So first of all, I'm gonna just care about the graph. And then I'll decide when it is greater than 0, right? When it is above the x-axis. So we graph standard way, we look at denominator and we say our domain means that denominator is never ever 0, right? And then x is not equal to -1. And this is great start because we already know that -1 for x will give us this nice vertical asymptote. So the next step will be to look for the horizontal asymptote. And notice that since powers of x and on the top and on the bottom are the same, I say that a quotient of these coefficients will be exactly my horizontal asymptote. And it's always like that. You have same powers of x, then to get the horizontal asymptote, you just divide or produce a quotient of the leading coefficient. So that's horizontal asymptote, quotient. So next step will be to get a point of intersection with x-axis, right? So-called x-intercept that tells us that y needs to be 0, and that automatically makes my numerator equal to 0. Denominator is not 0, right? It's out of the domain, so I just need to care only about my numerator. And that tells me that x is equal to 3. So someplace here is the intersection of function with the x-axis. So now I need to produce the graph. It looks like very naturally we go along the horizontal asymptote and down along the vertical. And analogously here, so I go upwards and to the left. I must be in that place because if I'm going down, I will intersect my x-axis again, and that's not allowed because we found only one point of intersection. See, that's why it's very important to actually find the point of intersection with x-axis, because there are no others. So we're done with graphing, but now the main question comes. When is it greater than 0? When this graph is above the x-axis. Well, this portion of graph is above x-axis, as well as that portion. You see that? That portion is also above, without 3. 3 is out. So from 3 to the right, or people say for to infinity, that's my one piece. And the other piece is starting at -1, right? -1 is out, and all the way to the left, so to negative infinity. The point is, once you graphed it, you're pretty much done, because all you care about is just to see when it is above and when it is below the axis. Let me graph one more for you, and then you will tell me when it is above and when it is below the axis. How about that? Or maybe not. Maybe I will just do it myself, the whole thing, because I think it may be a little bit too much with that. And then I'll do something else, because it's just too much graphing of the same stuff. Maybe I'll just do something else. Yeah, I think I better just move on, because we just keep doing the same thing. We did it last time, we do it again. One may wonder, say, Alex, is there anything else we need to care about? And it turns out we need to take a look at the next chapter that talks about logarithms. I just want to start the story of logarithms to, well, introduce it to you. I'm sure you already saw word logarithm in the previous math class. And so says Alex, I didn't take the previous math class, which is fine. I will start it from scratch where the logarithms start. I think I just got carried away and went too far. I think it's in 5.4. So I'm moving to chapter. Let me see, where do I move? I think it's 5.2 actually. I think I was just not careful, just skipped too many sections. 5.2. Is it? Where are the logarithms? So we have, oh yeah, yeah, first two sections, they have nothing to do with the story. 5.3 is what we skip. I think it's 5.4. I guess I got carried away. So yeah, I was there. So I just want to go to the section with logarithms. Okay, 5.4. So that'll be our next section to look at. So in the section 5.4, they're talking about such things as let me say, 2 to the power of 3. What is it equal to? 8. 2 times 2 times 2 is 8, right? You can rewrite this differently. You can write this as a logarithm base 2. So this number 2 you put as a base. Taken of number 8, that's the result. And that 3, that power, is going to be on the other side. So these two are exactly the same expressions. One says 2 to the power of 3 is 8. The other says logarithm of base 2 to produce 8 is equal to 3. So it's a power. Logarithm is a power. I guess that's all one needs to realize to feel comfortable working with logarithms. You need to know what they are. They're powers. So this expression is for the power. So if I want to see what logarithm base 3 of 9 equals to, then what I need is to get a power to raise 3 to get 9. What power is that? Let's see, Alex, 3 squared is 9. So it's 2. This is it. So we want to get used to treating those logarithms as powers. So what's logarithm base 2 of 16 equals to? Well, right away, I'm thinking about power of 2, right? The base is here. The result is 16, and the power needs to be number 4, because 2 to the power of 4 is 16. So the logarithm, the power is 4. So that's the, I guess, start of the story of logarithms that we're going to be dealing with till the end of this class. So let me take a look at some exercises here at the end of this section, 5.4, that actually want us to write this to the form of exponents. Like, for example, problem number 10 looks like is what I just did, right? So if we have an exercise number 10, given the 16 is equal to 4 squared, then we can write it as logarithm base 2 of 16. Or if you do problem number 17 that says logarithm base 2 of 8, well, we just done it here. It's logarithm base 2 of 8 equal to 3, that I can write as 2 cubed is equal to 8. How about number 18? Let me do number 18. Let's just stick with these for now. I just want you to get used to the logarithms. So logarithm of base 3 taken number 1/9. How can I write this as a power? Well, 3 is raised to some power that produces 1/9. I say 3 squared is 9, so it has to be a negative power. Because when you have a negative power, it's the same as if I have 1/3 to the positive power. So the result is -2, as we are actually given here anyways. Let's do some more. Let's get used to this a little bit better. I think this section compared to the previous is nicer because look at these problems. They're so much shorter, right? So I know that students prefer to do nice and short little exercises. So let me do problem number 25. Another recommended exercise here. Problem number 25 says, how about logarithm base 2 of 1? So I need to think of the power. I have to raise 2 to produce 1. So what power of 2 gives me 1? What do you think? Isn't that 0? Right? 0 power of 2 is 1, so the logarithm is 0, because again, the logarithm is power. So how about problem number 26? Logarithm base 8 of number 8. Again, I don't want to think too hard. I just present it as a power of my base, which is 8, some power to produce the same number 8. You say, Alex, you already have 8. Well done. So what's the power? 1, right? First power gives me the same thing. So it's power of 1. I say, there is no way you're going to do 31 that has square root. Well, can I think of a square root as a power of 1/2, right? Let me do one more for you here. Number 31 says logarithm of base 10 to produce 10 raised to the power of 1/2. Instead of square root, I put the power of 1/2. How about that? So I have to take base, raise it to some power to get power of 1/2. We see, so the power is 1/2. Yeah, so put 1/2, right? They ask, what is the power? So it's 1/2 power to produce 10 to the power of 1/2. So the logarithm is going to be 1/2. Just like that. So I need to make an announcement about next week. Do you know that there is no class next week? Say, how come no class? We were looking forward to it. Well, next Saturday is a spring break. Never heard of that. Spring break, not from my other classes. Well, spring break in our college is very unusual. Spring break is on Friday, Saturday, and Sunday. You say, well, Sunday is Sunday anyways. Yes, but Saturday people and Friday classes are not in session because of a spring break. I can actually see this. I found it here for you. I was looking for that in the calendar of our college. So it says for the spring term, they run in a spring break, which is very interesting, short recess. It's on April 7, 8, and 9. So Friday through Sunday. So Saturday is April 8, spring recess. No class. And next time we're going to meet on the spring 15, on April 15. April 15 will be our next class meeting. So you're not going to have a class for 2 weeks. Can you imagine that? 2 weeks with no math at all. Disappointing. Anyways, let me do another exercise, and then you can also try one for practice. So I'm going to do another exercise here, like problem number 35. I want to tell you a little story about a very special number called E. E? Why is it a number? That's a letter. Well, it's also a number. E is 2.718, etc. 2.718, ... It's just like number pi. Remember 314 something? But it's called irrational number, so it's an infinite number. And it's called as E. So if you have logarithm of base E, then you have a special name for it, ln. So instead of writing logarithm of base E, turns out this logarithm is so popular that they produce a special name, which is ln. So if I try exercise 35, that says find ln of square root of E, what I can do is prepare it as a logarithm base E of E raised to the power of 1/2. Notice that square root is a power of 1/2. So what is this equal to? Well, base is E. The result is E to the power of 1/2. So what power of E is that? We say, well, it's a 1/2, right? So the power is 1/2, and that's what my logarithm is. So how about problem number 27 for a quiz? I'm sure you're gonna like this 27. That's probably the first thing you learn when you study in the timetable, right? Like 5 times 5 is 25. So that's something similar to it. So the equation is What is this equal to? Tell me the result for this logarithm, and that's gonna be good enough for today. So put this